Now we can also think about these same three examples using different system boundaries. So instead of thinking about the person actually crossing the system boundary, let's think about a system boundary that just surrounds the sled, right? And let's think about what must happen to the momentum and the mass and the velocity of the system in those cases, right? Well, if we draw that as a system boundary, the mass does not change in both cases. So there's zero change in case 1, zero change in case 2, zero change in case 3, because we've said our system boundary is actually the sled, right? And the sled is not changing mass at all. It's true someone's riding on it or not, but the actual sled is not changing mass. The momentum of the system in the x direction, well, let's think about that for a second. The mass isn't changing, but what is happening is that there is an extra interaction going on. So before the person jumps onto the sled, the free body diagram for the sled is simply gravity and the normal force. But when the person actually lands on the sled, there's quite a bit more happening. So let's think about case 2 first. To think about that, this person lands on the sled. When they land on the sled actually has to accelerate them forward in order to have them stick to the sled. If they stick to the sled, that means that there's a frictional force between the person and the sled. That frictional force accelerates the person forward and accelerates the sled backwards. So the momentum of the sled must decrease. There's an interaction that's in the negative x direction, right? So if I draw the free body diagram, there's a frictional force that's acting on the top of the sled to the left. That's going to mean that the momentum in the x direction decreases or becomes more negative. I can make the same argument here in case 3, right? In case 3, when this person lands on the sled, pretty clearly, in order for them to stick to the sled, the person has to be accelerated in the forward direction. That means that there is a frictional force on the sled in the negative direction, and so the momentum must decrease in this case. And finally, in this case, if the person is actually jumping faster than the sled is going, when the person lands on the sled, they do so, and the sled must exert a negative force on them to slow them down to the sled speed. The sled at the same time experiences a positive frictional force, and so the momentum of the sled in the x direction increases. And finally, you can think about velocities in these three cases pretty clearly. If the momentum is increasing and the mass is not increasing, the velocity in the x direction must increase in the first case, must decrease in the second case, and must decrease even more in the third case.